So what we have left for you here is now the final stop of the whole thing is about a device that can store charges. All right. And that's kind of cool in the sense that because sometimes you want to, store your charge and then use it later. All right. So the idea is simple. I think the device that you probably have seen a lot that utilize this capacitor things that can store charge is defibrillator. เครื่องปั๊มหัวใจ All right, so that's the one that they use. When they touch those two pieces together, that's when they charge up or build up the amount of charge on the device. And once these two probes being put on the patient's chest, and that's when they release all the charge. And that's how they sort of like start up your heart again, on and on. That's how it works. All right, so you charge up the amount of charge on the device and supposed to discharge. Throw everything onto the patient's chest. That's what it is. All right. So how can we build that kind of device? That device, its name is good. It's called capacitor. So that's ability to store charges. And we're going to quantify the ability to store charge by this parameter called capacitance. Okay. So that's how big it is for you to store charge. So the bigger the C is going to be the one that we use as a notation for that capacitance. And because it's very commonly used, sometimes you're not going to even speak of the capacitance. You can call it the C of the capacitor. That's how common it is. So the bigger the C, the bigger the tank. Think of it that way. All right. If you have a tank to store charges. All right. But the way that you can build this one is very, very simple, guys. This is it. Okay. The thing is, every time that you want to store charge, usually you have to extract charge from somewhere. So that's why if you introduce positive charge on one place, usually there will be some deficits of that charge on the other side. Does that make sense? All right. So that means like everything is neutral at the starting point, and then you steal some charge to store it on one side. If this one is positive charge, then the other one will go negative, equal amounts. So that's why the structure of capacitor looks like this all the time. There will be the same amount of charge. One side is positive, the other side is negative. But now the thing is, we have already built up the understanding of this whole thing. But if you have a positive here, negative there, there will be electric fields coming out from the positive ends on the negative ends. Yeah. So that's in the sense of electric fields. But you can also speak about this in terms of the potential difference. We already learned that, electric field and potential are related. So that means you can also say that there will be a high potential on the positive side, low potential over here. So that means between these two, you will introduce potential difference. That's fine too. They are all, same business, just different perspective. And because people just, I think, just too lazy to talk about the difference, sometimes you might not see the delta anymore. I think เขาขี้เกียจพิมพ์ I doubt. So they're just like, okay, drop that delta, because everyone knows usually we're not going to do any potential by itself, right? It's always some difference between 2 points. So they just drop the delta, call it as V, but they are the same thing. So you're going to put delta there or not, same idea. All right, so think about it, Bojan. How can we quantify the ability of this device that's storing the charge? That's kind of easy. You think about it, the more of the potential difference, the more of the charge you're going to get, right? With me? Because if you have the big amount of charge on here, you're going to introduce even greater difference between two sides. So that means you're going to receive greater amounts of potential difference. So it seems like the Q and the V are going linearly together. The bigger the Q, the bigger the V, the bigger the V, the bigger the Q. So let's do that. We're going to turn that into just a simple relationship. Q is proportional to the V. So turn that into an equation, introducing a parameter C in between. That's it. That's how we define capacitance. Or you can think of this in terms of, all right, if I want to like show off this C a little bit, it's just the charge per volt. So if you have a capacitor that is big per volt, per voltage, then you're going to get a big amount of charge. So that's means you have a big tank to store it, right? Just introducing 1 volt, oh, we get a big amount of charge. So that means that's a huge capacitor, all right? So that's what it is. Units is easy now because its charge is in coulomb, potential difference is in volt. So is the Coulomb per volt. We have a special name for it. It's farad right here. All right, so that's cool. So the figure on the lower right corner showing you that common shape of capacitor. Have you seen this before? Yeah, right. In motherboard, main board in the computer, in electronic circuits, you're gonna see some of this, right? It might look like a coin shape, but most of them could be like a cylinder type. All right, it could be like a complicated one when you have a variable type. But if you read on it, this is it, guys. 4,700 microfarad. That's it. All right, this is how big is this dude over here. And some of this can be read here. All right, I think this one here, 100 microfarad, smaller. So you have a smaller tank. That's kind of okay. All right, so the shape is smaller, so it's supposed to have a smaller capacitance. Yes. I think they have to make it look like candy. Like M&M. That, well, not so sure why, but I think it's just the shape of the capacitor. That I'm going to review. Actually, that's a good question in the sense that I think it's easier to manufacture and because of the symmetry. And here we go. I'm going to review the shape of it. The common shape, I mean, not common shape, common structure of the capacitor is this, guys. See this? All right. But of course, the candy one, maybe they just use a circular path instead of the rectangle. That's all. All right. But the idea is this. It goes like this. The easiest way to create a capacitor is 2 plates. That's it. That's how easy it is. So whenever you have 2 parallel plates, metal plates, it could be aluminum, whatever, zinc, anything. You have a capacitor already. Okay. So think of it. If you have 2 plates, like a sandwich like this, and then you apply potential difference. Bam, bam, bam. Okay. So you can put like a positive polarity there, negative down there. That's a symbol for that battery. Think of it that way. So you can turn the upper plate to be positive, lower plate to be negative, right? Once you introduce a potential difference, now the charge will move from high to low. So that means eventually the upper one will go positive, potential. The bottom one will be lower in potential. All right. Once you do that, now I can disconnect this, bam, bam. Then you get a capacitor with a charge inside. That's how it is. And then you can bring this to anywhere you like, and then you discharge on it. Okay, so that's how easy it is to build a capacitor. That's very easy. However, that gives you a cautious sort of like statement. Every time that you see this kind of device, all right, on the electronic board, it's no big deal because this is look like a tiny piece of capacitor. That's no big deal. But you might have this big canister, like it's like a can, like this big. All right. Don't touch it. I mean, you can touch around it, but don't touch the ends of this too, because you don't really know is this has already completely discharged or not. Yeah, and it's so dangerous. If it's big, it means the capacitor is a very high capacity, right? And if it's still have some charge left on there, it can discharge on you, and that's how you pump your heart. You get electrocuted that way easily, right? So I mean, on the circuit boards on the stuff, it's not that bad because this capacitor is just to, maybe they use this to filter the signal and all the stuff, make it cleaner, make it, you know, smooth and all the stuff. But for the bigger one, actually you use it to regulate the AC circuits and all the stuff. So that's why it's big. This one, you can see it if you go out and look at the coilon, the air conditioner stuff. Inside, there is a big canister of this. All right, and the capacitance is somewhere, I don't know, maybe microfarad and all the stuff is huge, and that's very dangerous. All right, so be careful with this. Always, actually, don't touch. It's the best way. Don't try to discharge it. I don't think it's easy if it's big. All right, guys. So that's what it is. Now, it might not be in the shape of a parallel plate. It could be a spherical shape, but the key structure of it is you need 2 sides, one positive, one negative all the time. Okay. Or you can think of it like you have a parallel plate and you wrap around into a spherical shape. That's fine. It's still parallel plates anyway, but it's in a spherical shape. Or you can wrap that into a cylindrical shape. That's fine too. right? But as you can see, you need a positive one and a negative one. So there are always two sides all the time. All right, so what we're going to do is this. I am going to show you how to calculate the C of these capacitors. All right, but just once again, I don't want to go through all this because it's going to be a lot of calculations. I am going to focus on this parallel plate because it's easy. It's easy to see, easy to calculate, and just this, because we already learned a lot about this spherical shape, it's easy as well. So these two are easy to calculate. This one, well, I can do it, but well, it's gonna take a lot of time because the shape is weird. You need a different geometry. So don't worry about the spherical shape just yet. So we're gonna start from this. The way that you can calculate capacitance, I break it down into 3 steps. 1, 2, 3. If you look at these 3, see, love it. Gauss's law, potential, electric field, and capacitance. See, so this is a big finale over here, guys. We use everything that we have learned. All right, but don't worry. Well, we're not going to go through all the stuff like that, but at least the idea is there that the reason that the textbook write sort of the material in this direction is because you need to understand all those stuff before you can attack the capacitance calculation. All right. So what about those 3 steps? First steps, you use Gauss's law to try to find the electric field. What does it mean by electric field? Think about this, guys. When you have upper plate to be positive, the lower plate to be negative, you already introduce an electric field from top to bottom. You guys with me, right? Okay, so that means you should be able to calculate the electric field in between the plates. But then you already learned from the day that we did the potential, every time there is a field, there is a potential difference. So that means from that field, you will be able to calculate the potential difference between those 2 plates. And that's it. The last step is the easiest. You take that delta V, plug it into the definition of the C, bam, you get the capacitance of that piece. Done. All right, I'm going to show you right now how to do it. But the hardest part is applying the Gauss's law on these plates. We're not going to do it because I think you're going to hate me for the rest of the semester and other stuff. Take the answer. I think you like that better, right? But imagine this. If you have like a wall of charge, think of it like this wall is positive charge. Oh, I'm actually, this one is better because we want a piece, right? Here we go. Right? If this is a piece that I distribute the positive charge on it, I'm standing over here. I say, hey, what is the electric field at the tip of my nose? Something like that. Okay. So if you want to do Coulomb's law, you're going to have to do KQ over R square, KQ over R square, right? Right. And they're going to have like a lot of vector going on the tip of my nose and do the vector summation. That's crazy, right? So in general, because this is like a big piece of charge, you are better off to do the Gauss's law. But because I don't want to bother you with that anymore, so don't worry about it. I claim this right away. This is the final answer. Guys, the answer is this. If you have a wall of charge, you're standing in the front, the electric field is simple, sigma over epsilon naught. How nice is that? What is sigma? You sort of like saw that a couple of times. The sigma is just the charge density. Charge over area. It's 2-dimensional, right? So that's why it's just a sigma. All right, so that means the strength of the electric field depends only on the density of the charge on this piece of charge. That's it. So that's kind of makes sense, right? The more charge that you have, the higher density of the charge you have, the higher electric field in front of that. So that's perfect. All right. However, the complication is this. This formula is being used in a realistic fashion because usually you will find that you usually do this on a conducting material like metal, you know, aluminum, iron, and other stuff. So what you have over here is usually you build up a cage of charge. It's general, it's like all the charge are on the surface. And we just learned from before the break that the electric field inside is always 0. Inside any cage, right? Any charged cage. So that's why this electric field only point in one direction, outward. Why do I have to mention this? Because I am about to build the parallel plates capacitor for you. And let me ask you one more time, what should be the electric field that I'm going to show you right now? All right, guys. So in conclusion, that's it. You can take it here. Electric field from a conducting plate is sigma over epsilon naught. Keep in mind that is only one side. Okay, it's pointing out the inside of the metal, there's no electric field. But what I'm going to show you is this, guys. Here we go. The textbook sort of like bring you all crazy stuff, doing Gaussian surface in the different shape, blah, 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 blah. Okay. No, I don't want to do that. It's too complicated. Let's do this. Almost done, guys. Here we go. Let me look at the upper plates. Let's imagine that this is my positive sheet of positive charge. And the bottom one is a sheet of a negative charge. Sounds cool? All right. Okay. So I think the easiest way to do this, let's do this from a blank sheet of charge so you won't get confused with what you already had. So let's imagine that I have only a single piece of positive charge. What do you think it will happen around this? But oh, Dan, this is easy. Because this is a blank, like a tiny sheet of charge. So now you're going to generate electric field on both sides now. You guys with me? Cool. Okay. This is kind of, I try to make it uniform over here. Okay. All right, cool. So can you answer me what should be the electric field coming out of this? What do you think, given the formula that you just got? So this one is different, right? Because I have just a tiny piece of charge, right? It's a super thin sheet, okay? So that's why electric field now point in both directions. So claiming from the result that we just got, electric field on this one supposed to be, well, units supposed to be the same, but then you have a factor of 2. You guys with me? Because now you split on both sides. Back in the day of this, it seems that you have only one side, so you have only sigma over epsilon naught. Okay, but now you think about it, you have to distribute this on both sides. So now each side will get half of this. Sounds cool? All right, so that's why for just a simple piece of sheet of charge, which is 2-dimensional sheet, what you get is sigma over 2 epsilon naught. Cool. But then, that's not the device yet. The device needs to be combined with the negative side of this. So I do that too. So let me overlay on top the negative one. Why this is so big? Oh, there is an opacity. Okay, that's why. All right, here we go. So now I have a negative charge waiting for you down here. All right, so negative charge will generate its own electric field, but now because it's negative, so it's going to point into it. Make sense? In, towards it, towards it, towards it, towards it, towards it. Yeah, cool. But how much, guys? What should be the strength of this whole thing? But exactly the same. So for the red one, the upper side of this is sigma over 2 epsilon naught. The bottom one is sigma over 2 epsilon naught. Same thing, but it just points in a different direction, opposite direction. Cool? Okay. What should be the next electric field around this device? Can you see it now? Look at the upper portion, guys. Upper portion. Around up here, see that the red is down, the blue is up, same amount. So that means you get a cancellation of everything. With me? 0, yeah. What about the bottom? Yeah, right, because now the red is up, the blue is down, same amount. So you get cancellation effects down here as well. The only thing left for you to be non-canceling, but actually adding, is the space in between. They're both pointing down. But because they're pointing down with the sigma over epsilon naught over 2, you add them up, you get back the original value. And that's it, guys. It's done. So in conclusion, whenever you have a parallel plate capacitor like this, like that, you're generating an electric field in between. Bam, bam, just that. Electric field only happens between the plates. Okay. ไม่ค่อยสมูทเท่าไหร่ แบงค์วาดสวยๆหน่อย Okay, here we go. All right. ไม่ค่อยสม่ำเสมออะไรนะ Okay. It's supposed to be pretty good. Okay. And the value of this is E is sigma over epsilon naught. Again, perfect. It's done. So that's why, I mean, the result, I mean, the formula wise, it looks exactly the electric field from the conducting metal and all this stuff. But I mean, all right, you don't need to worry about that much. This is what we care about. เกือบจบแล้ว Do you see what I see? This is step number 1. You found the electric field inside the capacitor, right? Step number 2. Can you figure out the potential between the upper and lower plates now? How much is the potential? You know the E. How can you figure out the V? Exactly right. Very good. So delta V is E times D, because think about MGH, right? The GH, that's exactly as a E times D. That's a potential. Very good. So that means if I know the distance between the plates, all I have to do just multiply that by the D, the distance between the plates. That's a step number 2 already, guys. This is number 1. This is number 2. And what about the step number 3? By definition, it's just a charge per potential difference, right? So you just take the delta V from the second step, plug it into the third, which is just a definition of it. There you go. But then, Mojan, wait a second. You just told us that the sigma is just the charge per area. So that means if I replace this sigma with the Q over A, so the Q will cancel. So I don't have to worry about the Q. I only worry about the size of the area. That's it, guys. That's the final formula for it. And that's how you figure out the capacitance of a parallel plate capacitor. All you care about is what is the surface area, what is the distance between them. And one thing that is very sort of like a very obvious characteristic of this is it depending on the shape of the capacitor. If you use the same area, same distance, the C will not change. Okay? The only way that you can change the C is you have to change the physical parameters of this. Where have you seen this in your life? You are using this almost every day. The what? Car battery. Okay. The battery is not capacitor because it gives off the uniform voltage. So they use the chemical reaction to give you like 12 volts all the time. But this one is not going to discharge 12 volts. It's going to give everything, and that's it. It's done. It's going to deplete itself. Yeah, and like to use that to start the car, you just want to release the whole thing right away. But the battery is like constant voltage, right? You can use it for a long time. It's slow release. What have you used this almost every day, or maybe every day, I think? The phone. Yeah, you use the phones every day. And that will be the climax of today's lecture. But that's not for this one just yet. Your phone all use the same property, but not by the same underlying reason. What are you using that utilize this properties? Or more hints? Use your finger as well. Touch screen, not yet, because you haven't changed anything on the touch screen, right? You cannot change it. What can you change the physical parameter of this? With your finger. Yeah. So every time you punch the key on the keyboard, you change the D. Yeah, the membrane inside the keyboard down there. So that's why the keyboard don't need electricity, because they only detect the change in the C. So the key that changed the C, that's the key that you press. Cool. All right. So that's what they are have using these techniques all the time. So if you tear up the keyboard, back in the day, the membrane is kind of huge, I think, and they even don't care about the material usage. They put like a two plates, parallel plates on there. You can see like there are two membranes in there. But nowadays you can reduce that material usage a lot because the membrane just on that key. Because why you have to use the whole plate, right? Because the key is only tiny. So they have like a private parallel plates on each key. All right. So every time that you press it, you just change the C. Cool. All right. So that's the conclusion, guys. So this is what you have. 3-step process give you the capacitance of this. But then now think about it. The idea is now simple. 3 steps, just break it down just for you. First, you want to figure out the electric field from Gauss's law. Second step, you utilize the concept of the potential difference derived from the electric field to get to the delta V. And the third one, plug in the delta V into the definition of C. That's it. That's done. All right. It looks like complicated, but it's not. And here comes the question in the exam. จบเลย Find me the capacitance of a spherical capacitor. Using, you can use the 3-step process or not, doesn't matter. But in the exam, I'm going to ask you to show me how it's calculated. And of course, you know the final answer already is right here. There you go. Cool. All right. So the reason I want this because, you already know how to calculate electric field from a spherical shape using Gauss's law. We just did that. So that should be easy. And the hardest step will be the step number 2. Once you know the electric field, how can you figure out the delta V between those two concentric spheres? And the last one is the easiest. Once you get the delta V, plug it into the third, you will get the C. And you try to get to this final conclusion over here. Sounds cool? All right. And of course, this already on any textbook in the universe here, so you know how it's done. All right. But anyway, look at the formula, guys. What do you see? It's once again, depending on the shape. See that? The formula depending on the A and B. What are A and B? A is just the radius of the inner ball. The B is just the radius of the outer shell. That's it. So you just once again seeing that the capacitance depending on just the shape of the device. The only way that you can change the C is you have to change the size of the spheres. If the spheres stay the same size, the C will not change. Okay, cool. All right. And for this cylindrical, don't worry about it. All right. We don't do the calculation here, so you can ignore this calculation. But I want you to look at the final result once again. Confirm. All right. If you just take the formula and look at this, once again, it's only depend on the physical shape of the device. How long is the cylinder? What is the A and B? And A and B is once again is the radius of the inner cylinder and the outer cylinder respectively. See, so once again, it's confirmed. The capacitance is being determined only by its physical shape. รูปร่างเป็นยังไงมันจะเป็นตัวบอกว่า capacitance มีค่าเท่าไหร่อย่างนั้นเลย easy. All right, so that's where is a good conclusion here. All right, and you got 1 problems to go into the exam now. So that's 10 points today. คุ้มวันนี้วันเดียวคุ้มไม่ต้องเรียนวันไหนเลยเอา2 โจทย์ข้อนี้เข้าห้องสอบก็คุ้มแล้ว All right, 2 questions in the exam. However, บอกอาจารย์ wait a second. That's going to be crazy if every time that you want to change the C, you have to change the shape because sometimes it's not easy to change the shape, right? So if you want to increase or you want to enhance the capacitance, you have to change the shape all the time. It's going to be crazy and it's not going to be easy to do. Are there any other choice that you can apply? All right, so I'm going to bring in the last slide of the day, guys. Here we go. All right, so this one is on the last handout. And the good news is we're not going to have time to do all the circuits analysis. I think you like it, right? I don't know if you like it or not, but we're gonna just finalize our trimester with this one, the last stop of the capacitor, guys. Here we go, almost done. What we have done so far, we just assume that the space around the capacitor is just blank space, vacuum. We haven't explored the possibility that, why don't you put something in between? Change the environment a little bit. Would that work? Oh yeah, because in reality, you don't want this because this is kind of like you don't have any reinforcement between the plates. So those two plates can touch each other and then you short the circuits and everything that's going to go bad, right? So, I mean, you love it to have some things to support between them. So that's why if you tear up the keyboard, you look at the two membrane, between those two membranes, there will be another membrane in between. All right, so that's good. At least it protects those positive and negative plates to touch each other. That's one thing. However, scientists and engineers is even more clever than that. They can introduce another kind of material that has an ability to enhance the C along the way. That's kind of nice. What does it mean by that? If the material that you squeeze in between is a dielectric material, now you're probably wondering what is this? Remember from chemistry, a polar molecule. Kunไหม? Molecule มีขั้ว sounds reasonable. Have you heard before? If not, that's okay. Water, guys, water, H2O. Everyone knows it's a neutral molecule. But in reality, in the language of chemistry, they said oxygen has a higher electronegativity. คุณคำนี้ไหม? So it means electrons seem to spend more time on oxygen atoms than hydrogen atoms. So that means all the oxygen ends seem to be a little bit more negative than the hydrogen ends. All right. So if I sort of like demonstrate this one in terms of like a diagram, it will look like this. If I put this in like just a simple diagram, oxygen side will be a little bit more negative than the hydrogen side. Okay, so it has some sort of like a directional in terms of like, all right, it's positive at one end, it's negative at the other end. In a regular condition, nothing happens because there's no control. This molecule can point in any directions randomly. That's no big deal. But the thing is very interesting when you put these molecules under external electric fields. What do you think it will happen? It's going to happen just like the compass in in a magnetic field, right? Your compass always point north, right? Because that's on the magnetic field. Same thing over here. Because you have charge under fields, they try to move. So that means the positive charge will try to go along the field. The negative charge will try to go against the field. So what you get is now you get a compass behavior. All of those molecules will try to arrange themselves along the electric field that you put in. Sounds cool? And what is the final effect? This is very cool, guys. And this is amazing. Those that found this one out is very, very good at utilizing physics here, guys. So the cartoon version is this. So think about it. Now all of the molecules inside are oriented along the external electric field, right? But now you think about it, you have Avogadro numbers of this. It's like million of molecules. So that means every time that you look at that, a positive side of the molecule, there will be a negative side of the neighboring atoms to cancel the effect all the time. Positive is going to be near to the neighboring negative. Positive, there is a nearby negatives. Positive, nearby negative, positive, nearby negative. All of this stuff keep canceling each other inside the material. Can you see that? Yeah. However, if you look carefully, this one don't know what to do with it. That side cannot cancel with anything. Can you see that? So it looks like anything inside seems to have its neighboring atoms to cancel the charge with, but the surface cannot. These dudes over here, the negative one is sort of like hanging there alone by themselves. They don't have any neighboring positive charge to cancel. So you can imagine that the left surface of this material is going to be negative charge. Same thing happened on the other side. The positive ends of this one don't have any neighboring atoms to cancel the charge with. So it's going to be positively charged on this surface. What do you see here? Wow. So by having the capacitor, right, outside, and then you squeeze in the dielectric material, you induce another capacitor in it. See that? You have a positive plate on the left, negative plate on the right. You squeeze in the dielectric material in there. Now you have another capacitor inside the green one. You see that? However, this inside capacitor is pointing in the opposite direction because it's positive on the right and negative on the left. So that means this induced capacitor, that's my word. อย่าไปใช้นะมันไม่มีใครเรียกว่า induced capacitor นะ But anyway, the point is that induced portion of the capacitor, here, let me draw this one down here. There you go. Will also generate the electric field pointing in the opposite direction. Can you see it now? Yeah. So the outer plates have electric field point from left to right, but you already induce it's all like, you know, another capacitor that's opposite to it. So it will generate electric field pointing opposite to the external field. So when you have a net electric field in between, you're going to have a tiny amount left. I mean, smaller amount. The net electric field will be smaller once you squeeze in the dielectric material in there. And you see what's the point now? Almost done, guys. When you already have the smaller amount of E, so we have E, E getting smaller. The delta V will also get smaller, right? Because they go hand in hand. But from the formula, C equal to Q over delta V. When delta V is smaller, what happened to the C? That's it. That's how you enhance the C. All right, one more time, just recap what we are doing over here. You have an external field from the capacitor itself. You squeeze in the dielectric material. Those molecules line up, but lining up those molecules end up with an induced capacitor inside. That's point in the opposite direction. So having the net electric field in between to be smaller. So when the field is smaller, the potential difference will go smaller as well. So when the delta V is smaller, you get a bigger C. You're done. All right. So the only last job that you have left is how much bigger, right? Okay. Right. Okay. I know it's bigger, but how many times bigger? It depends on what type of material you introduce into it. And you will be surprised how easy it is to do this. The material can be characterized by something that's corresponding the name with the dielectric material. You have the name of dielectric constant. Okay, dielectric constant. So that means here, guys, this is a table. Oh, how come I have two of this? All right, okay, I'll come back to this. Here, you have a table over here. Can you see this? The air have a dielectric constant of 1. This means there's no change. But then if you go up down here, water, look at water. Whoa, it's an 80 dielectric constant. In comparison to paper, paper has some numbers of this. So that means you can actually use paper as a dielectric material. And actually back in the day, I saw some keyboard squeeze in the paper in between those metal membranes. All right, so why not? All right, it's already can be used here. All right, but what are these dielectric constant is being used for? Guys, it's very easy. I'm going to show you right now. Here we go. จบแล้ว Very cool. If I have a positive charge Q, I am standing at a distance or away from it. Everyone knows E equal to K, which is now we introduce 1 over 4 pi epsilon naught Q over R square, right? Okay, everyone okay with this? No problem. If I ask you this, hey guys, actually this charge is inside a water. Oh, water is supposed to be blue. What do you think you have to do? Whoa. Whoa. If this charge is inside a water, I want to find electric field at the distance r from it. What do you think you try to, what should we do here? The answer is very simple, guys. Here. Bojan, E underwater, let me call E prime here. 1, look at this, over 4 pi epsilon water. Q over R squared. Is that easy? So now you know what the naught sign is for, the 0, the epsilon naught. That naught just say is a vacuum. If you have the space to be not vacuum, is water, find out what is the epsilon of that material. If it's water, you do epsilon water. If it's plastic, you do epsilon of the plastic. If it's glass, you find epsilon of the glass. Okay? And how can you figure out this epsilon water? It's just the dielectric constant multiplied by epsilon naught. It's done. Bam. So you see the utilization of the K now, the epsilon. I mean, this one sometimes they use kappa, which is a Greek, but I mean, it speak easier, just use K, dielectric constant. So that's it. So that table will automatically give you the epsilon of that material. That's how easy it is. So that means if you put this charge inside the water, and we just saw from the table that the dielectric constant is 80, so you just put 80 over here. So that means if you try to find electric field at the distance r inside the water, the electric field will down by 80 times. Okay, sounds cool. All right, and this is what kind of exotic about this one. If you look at the bottom of this one, see that there is some ceramic or maybe some exotic material that can enhance the dielectric constant to be like 100, 200, 300. And this one, I think, I don't know, you built PC back in the day, like maybe 20 years ago. So the main board back in the day, after maybe a couple of years, maybe 5 years, the capacitor is going to turn bad because there's some liquid leaking out. I don't know, have you seen those? Something leaking out, just like battery, bad battery, there's something leaking out. Because back in the day, the capacitor that used dielectric material that is made of liquid. And that liquid seems to go bad over time. But now, once they do this kind of ceramic type, so it's all solid phase. So it lasts like 10, 20 years without any problem. So that's why PC, desktop, and all this stuff nowadays, it lasts like 20 years. Easily, I think. You can still turn it on as long as capacitors are all good. All right. So that's why if you buy like a motherboard nowadays, they say it's a solid state capacitor made in Japan to make it like good quality and all this stuff. So that's it. So that means back in our business over here, Bajan, so what's changed to our capacitor? So the formula that you saw before, C equal to epsilon naught A over D. If you squeeze in the dielectric material, what do? Yeah, just turn this into, okay, let me write it. Turn this into epsilon of that material. And that epsilon of that material is just K times epsilon naught. You're done. See? So you just apply the same formula, but you just replace the epsilon naught with the epsilon of that material that you squeeze in. You're done. You can do this with every type of the formula. For example, even this one that we didn't show you how to calculate. The original formula of this one is 2 pi epsilon naught L over log B over A. If you fill this with something, bam, 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 all you have to do is just turn this epsilon into epsilon of that. And that is just kappa epsilon naught. Done. Okay, so the conclusion of this one is that's another way of changing the capacitance without adjusting the physical shape of this whole thing. All right, but this gives you one conclusion, guys. Now you can see that by changing the environment, see, from vacuum to something else, you can change the C, right? And that's what you just said to me. you actually use it every day on the smartphone. If you look at the box, the touch screen on the box in the specification, they say it's a capacitive touch screen. And they use the same techniques. All those pixels that you see on here, it's a capacitor underneath. So when you have your finger around, with and without your finger, you change the C as well. So that's how you detect the location of your finger on this screen. Okay, and I think this one is patented by Apple. The reason is, I mean, Apple wants this one because back in the day, you did the Nintendo DS game, yeah? If you remember the screen of that, it's soft screen. It's kind of like you can put a pen on it, right? There's a pen on it. And once you press on it, the screen will dent down a little bit. It's a soft, like made it from plastic or something. And that's because they use not the capacity, but it's a resistive. So that's why you need a physical change to change something. But the bad thing about that one that Apple don't like is you need a plastic, you need a flexible screen. And every time that you do a flexible screen, it's not going to be as clear as glass. So that's why Apple wants glass top. They want the whole thing to be glass, not plastic. So that's when you start doing this capacitive touch screen here. And once you have that, now multi-touch can be introduced easily because now you can touch multiple points at the same time. You can detect everything. But if you try to do this on the Nintendo DS, no, it's going to be tough because the accuracy will be really bad because you need physical dent to look for the position of that press. Yeah. All right. So that's what it is, guys. We use a lot of capacitive change nowadays. And with that, then even though you put like a mirror or whatever, like a glass top, you have like a, screen on top, you have a glass, you have OLED on top, you have S Pen layer. I don't care, right? Because all you care about is just a change in the seat with and without your finger. So that's why you can have this screen in all in one package. Is you have like a OLED display, you have a touch screen sensing layer, you have a S Pen layers on it, everything come in one piece. That's kind of cool. And on top, you slap on the Gorilla Glass, whatever, I don't care. And everything is good. You can put the film on top. You can slap on like, UV protective screen and everything. No, nothing is going to happen. All right, guys, that's cool. So that's it. I'll give you 2 examples. And I think you're going to love this because as you can see, it's non-technical questions now, as long as you agree with what we have here. You have a parallel plate air filled with a capacitance of, given this, 50 picofarad. Pico is 10 to the negative 12. It's 1 in 1,000 of a nano. All right, so it's 1 step smaller. So part A, if each of its plates has an area of 0.25 square meter, what is the separation? So part A is easy, it's plug and play. So C is epsilon naught A over D. So that means D is just epsilon naught A over C. And you just plug in the value, you're done. All right, part A is nothing, it's no big deal, John, that's fine. But what about part B? They say, if the region between plates is filled with a material with the dielectric constant of 5.6, what is the new capacitance? ง่ายไหม? Oh, well, John, that's kind of cool. We love it because the new capacitance is just going to be K times C. You're done. So we love this one. The reason I like this because even though the explanation is long, I have to talk about dielectric material. You have to understand the induced effect, whatever, the net electric field is reduced, blah, blah, blah. But at the end, all you care about is just substitute the epsilon naught with the epsilon of that material. And the epsilon of that material is just the constant K multiply. That's it. So that's why by introducing the dielectric material, if the dielectric constant is K, you enhance the capacitance by that amount as well. So we love it. Conclusion is easy, right? We kind of like it. Okay, guys, one last exercise of the course. Is this going to be your last physics course in your life? Is it possible? Oh, no. Okay. Oh, there's something else. Okay. Ah, physics lab. Oh, okay. All right. I thought it like gonna end with like a dramatic. Okay, guys, this is the last exercise of your life. No, okay, it's not. All right. Guys, try this. You have an air-filled parallel plate capacitor. Okay, has a capacitance of 1.3 pico again. All right, pico is 10 to the negative 12. The separation of the plate now is double. So somehow you separate them out. And then not only that, you insert wax in between. It turns out you make a measurement again, your capacitance is doubled. Find the dielectric constant of the wax. Ooh. Oh, you got the number already? Oh, no. All right. The way that I do this is, as usual, we love this. We saw this since the thermodynamic stuff. You just compare between one condition with the other condition. So what I can do is this. I can call C1 equal to epsilon naught A1 over D1. Cool? The reason I pick epsilon naught because in the first condition is still air filled. All right. And then I do the same thing with the new condition. Let me call it C2. Now your epsilon is changed to a new epsilon. So let me put epsilon there. You can change the area if you want, and you can change the separation if you like. And the way that we did all the time, just do the ratio, compare. So C2 over C1, and now I can group the same type of quantities together, make it easier to analyze. So it's going to be epsilon over epsilon naught. That's for the epsilon stuff. A2 over A1, that's for the area, and then D1 over D2 for the separation. Sounds cool? All right, to make it easier to analyze. Now, first thing first, this problem do not change any area. So actually, I can cross this one out. Area stays fixed. All right, and second thing that we know is because epsilon is simply just a dielectric constant multiplied by epsilon naught. So that means this ratio over here will give you K, the first one, right? And the D1 and D2, because you already doubled the plate separation. So that means that one will give you 1/2. The last one here is 1/2. Cool. And now because at the end you double the capacitance, so this ratio must give you 2. And that's it. At the end, the K is 4. You are done. That's the K of the wax. All right, so I hope you don't have to worry too much about this stuff. So the last question in the exam will be kind of easy now, because once you know the formula, once you understand that what is epsilon versus epsilon naught, that's easily used. Yeah, don't have to worry about the detail and all this stuff, except the question that I told you. All right, guys, and that's it. That's a wrap, guys. Thank you. All right, so that's everything is done over here. All right, so don't forget, you have, oh, it's not on this slide here. All right, you have 2 questions in the exam. All right, make sure that you do that. Here we go. Yeah, find me the capacitance of the spherical capacitor right here. Show me the detail, how to get to the C value here. And the second one is find me the electric field inside a ball of charge, a solid ball of charge. All right, at least that's something that already know beforehand. 2 problems. All right, guys, it's been a pleasure teaching you. I hope you learned something from the course. All right, and well, no. All right, okay, but anyway, good luck. All right, and then I'll see you on Sunday, next Sunday, right? So on the exam dates. Okay, all right. In the meantime, if you have any questions, you can leave comments on the Google Classroom, and I'll try to answer that. And I will prepare the maybe the O exam. I'll do that, you know, give it you another shot on that, and then so we have some practice problems. And don't forget to do the exercises, and that's it. All right, guys, thank you so much. I'll see you around on campus. Yeah, take care. Thank you.